The action potential, that's what we've been leading up to here, talking about neural signaling more generally, the resting membrane potential, gradient potentials, and now we're ready to talk about the action, which is the action potential. So I actually want to go back and show you an image of the squid giant axon. And this is where the action potential was first discovered because the axon is so large. Researchers were able to impale it with an electrode, and they measured that not only does it have a negative resting membrane potential, so the inside measures negative compared to the outside of the cell. Also, there are rapid changes that occurred that they noticed. What are these rapid changes? This is an action potential. So what they did, and I drew this before, was measure the ions, the charge difference inside the cell versus outside of the cell. Remember, the outside is always 0. It's always just set to be 0. This told them the resting membrane potential was minus 70 millivolts. What they found, though, was not only that, but there was a rapid change at this time point that they're measuring. It went from minus 70 way up to plus 20. It became more positive inside compared to outside, and then back down again. And this is what an action potential is. And we'll, of course, look at how that happens, how it becomes more positive in there. Okay, so what I want to do is have you just brief review here. You should be able to answer these questions. What causes gradient potentials? Where do they occur? What do they result in terms of the change in the membrane potential? And do they cause an action potential? So please answer those. Okay, what causes them to occur? Opening of gated ion channels. Just the most general. If you didn't quite know how to answer that, that's fine. But it should make sense, right? Gradient potentials occur when ion channels open that had been previously closed. Where do they occur? Dendrites and cell body, right? They can result in either hyperpolarization, more negative, or depolarization, depending on which channels open, and therefore which way ions flow. Lastly, sometimes. That's it. So just to remind you, gradient potentials can result in action potential. A stimulus occurring at the cell body or dendrite results in the passive flow of currents along the body of the neuron. This passive flow is what's shown here, these positive ions that are just flowing locally inside the cell. If they reach the trigger zone, the axon hillock, and are still in substantial quantity, these ions actually reach that place, then that can cause an action potential due to these local currents that are ion movement inside the cell. Okay, so I think we're set to go ahead and break down the action potential. Let's do it. So again, remember, we are talking about the changes in membrane potential within one small section of the membrane. So just like with gradient potentials, we kind of just looked at the resting membrane potential inside and outside. Here we're going to be looking at changes just in one small section, what an action potential is. So the graph I'm going to draw is in one small section. We will then look after that at how this signal is propagated or conducted down the axon. First, that's what we're doing. Let's get rid of that for now. Okay, so I'm going to draw a graph for you. You can draw it along with me. First, we need some axes for a graph. You should be able to guess what these axes might be, how we would label these. Right, we're going to have time here on the x-axis. So again, this is not distance along the axon. This is just looking at over time at one point. Over here, we've got the membrane potential in millivolts. I'm going to write up membrane potential. And this title of this whole page here, changes in membrane potential during the action potential, should make sense. Changes in membrane potential, which is our dependent variable here, during an action potential, which is going to occur over time. A couple of key membrane potentials that I want us to have here. So I'm going to note those here, and you probably could guess what's one important membrane potential. It's going to be rest. So we're going to put -70 on there. It's one of the important membrane potentials that we need to, that's where we're going to start. What else? We're going to need a couple more. So -55 is a key one. That's actually going to be called threshold, where an action potential is going to happen in an all or none fashion. So this is threshold here. Actually going to do a dashed line for that if I can do it straight. Then we've got 0. So that's where there is no difference in charge inside and outside of the cell. And then the maximum I have here is +30. That is the highest membrane potential that's going to occur. Inside the cell will be +30 compared to outside of the cell. Okay, so at rest, change my color here. You know where we are. We are down here. I'm going to make my drawing a little bit fatter here. Here we go. We're at rest. And we stay at rest until we have a stimulus that is large enough to depolarize the membrane to threshold. So we can have a little blip here that then goes back down again. That was a graded potential, a local potential. But right now we're going to talk about a stimulus that is large enough to hit threshold and what is going to happen there. So between 1 and 2, to cause this to happen right here, what happened? I'm going to make a text box here for this because my handwriting is too messy. So this is time point 1. Just going to write like that. Move it over a bit. And what's happening at time point 1? We'll actually put it here. We've got some stimulus, gated Na plus channels open, right? If you open gated sodium channels, put it down there. Sodium is going to rush into the cell. That's going to cause the membrane to depolarize. So that's time point 1 there. We keep going. What color did I have here? Can't find my same color. So I'm just going to draw, oh, maybe this is black. Okay, it is black. We're going to keep going. This is our all or nothing. This action potential is going. We can't stop it. It goes all the way up to +30. Then we're going to go back down. But I want to label 2 more things here. We've got time point 2 right here. I want to label threshold separately from anything else. I'm going to label time point 3, which we will get to in just a moment. So time point 1 was stimulus opened. Time point 2, that stimulus opened and was sufficient. Threshold was reached. This means the voltage gated Na plus channels opened. Once you reach threshold, the stimulus is different. Initial stimulus is due to gated ion channels. What is that initial stimulus? Typically, right, let's put typically here a ligand. Is the initial stimulus. Once we reach threshold, it's going to be voltage gated ion channels, still sodium. So we still have sodium rushing in. That's why we're having further depolarization. So from actually, I'm going to move my 3 up to the top, because from 2 all the way up to 3, that's where those voltage gated sodium channels are open. At 3, we've got Na plus channels closing. And one more thing, we also have potassium voltage gated potassium channels opening. What happens when potassium channels open? Potassium goes out down its electrochemical gradient. So that's what's going to happen all the way down this way. We're just going to go through that. Here, potassium is going out. You can label it as a separate time point or not. You should know. I'll just put a note in right here. Leaving cell. Down its electrochemical gradient. At time point 5, notice there's an overshoot here. Potassium leaves the cell and hyperpolarizes the cell. This is time point 5, which I will make one last different color here. At time point 5, we've got the potassium channels close. We've also got, how do we get back to rest? Let's actually do this separately here. It's just after that. We'll put it right here. Is the K pump reestablishes resting membrane potential. Yeah, that is the action potential. And you should be able to think about where channels are open and closed and what that means for ion movements during each of these steps. Okay, let's talk a little bit more about this voltage-gated sodium channel. And I believe I'll do that in a separate video just to break things up.